Okay, I will start the class. Let the others join. Okay, later. Okay, some leftover topics is already I told you that state space models can be obtained using two sets of variables. What are the two variables with the help of which it can be obtained? This being the last class, at least please respond. I'm hoping all can hear my voice. So, what are the two ways in which you can convert a given system into a state space model using what sort of state variable? Yesterday's class I told you, no?
Physical and phase.
Yes, physical and phase variable. Okay, apart from this, you can also use another type of variable, that is canonical type of state model also you can use. Okay, under canonical you can have observable and controllable canonical and diagonal canonical. The formula alone will differ. Okay, the state space model formula alone will differ for all these things. So today's class we are going to discuss how to convert the state space model into a canonical, I mean how to convert the given system into a canonical type of state space model. Although I think it's not given in syllabus, still it's there. Okay, suppose in case if such problems are coming, you should be able to solve. So I am covering up this topic. So today's class we are going to learn out how to obtain state space model using canonical variable, that is observable canonical, diagonal canonical and controllable canonical. Okay, again I am telling you only the formula will be differing a little bit. Other things are always the same. So if you are assuming this is your given system which is given in terms of some polynomial representation where u is the control input and y is the output, and this is your transfer function representation for it, and you know the coefficients of the numerator polynomial and the coefficients of the denominator polynomial. So what are they as given in this equation? What are the coefficients of the numerator polynomial now? This is your numerator polynomial. So what are the coefficients for them? You people will respond, or shall I continue without asking anything from your side? Okay. Anyways, the various coefficients are b naught, b1, bn minus 1, bn. These are the coefficients of the numerator polynomial. In the same fashion, a1, an minus 1, an are the coefficients of the denominator polynomial. So using these coefficients, if you are framing the state space model, then it will be called as canonical representation. So we'll discuss what is the difference between observable canonical form, controllable canonical form and diagonal canonical form. We'll discuss how all those things differ. So first one, here comes your controllable canonical form. So if you want to obtain state space model in controllable canonical form, as I told you, you know what is state space model representation. You are to obtain equation of the form x dot is equal to ax plus bu and y is equal to cx plus cu. This is your state space model. I want this representation from the given system. So how I am going to do that is, I know what are the coefficients an minus 1, an minus 2. I just pick it up and I substitute in this diagonal system matrix. Then I will be able to get controllable canonical form. Same way I need to subtract the coefficients of the numerator and denominator polynomial. I will be able to get the C matrix. Okay, so this is the standard formula that you have to remember. Using this formula only you will be able to obtain the controllable canonical form. And you have to remember that the equation will be having 0 1 0 0, then 0 0 1 0. Like this only you have to represent the A matrix. Now if it is to be represented in observable canonical form, means you can easily observe the A matrices are different or they are same. The A matrix, B matrix, C matrix all are different from the controllable canonical form, or they same. One, if it is to be a controllable canonical form means here you will be having a, I think a coefficients, but somewhat it is differing a little bit. Now the A matrices, the coefficients are coming here as column, all right, and this difference was coming here in the C matrix. Now it is changed. So this changes you have to observe if you want to obtain the observable canonical form or controllable canonical form or diagonal canonical form. So these three formulae you have to remember. With these three formulae only you will be able to solve problems. Next comes your diagonal canonical form. Diagonal canonical form, if you want to obtain means you have to take partial fraction expansion. After taking partial fraction expansion, you need to determine what is C1, C2, Cn constants, then what are the poles that you are having, then what is B naught. With these, you will be forming the state space model, then it will be called as a diagonal canonical form representation. Like here, okay, this is your diagonal canonical form. This is the third formula that you have to remember. So based upon this formula only you will be able to convert the given system into a canonical model, canonical type of state space model. As I've told you, state space model in canonical form, three ways it will vary: observable canonical, diagonal canonical, and controllable canonical. For these three categories, the set of formulae for the state equation and the output equation will vary. That's the thing. Other than that, as usual procedure you have to follow. Now here comes a given problem. In the problem they have asked you, you have to obtain the state space representation of the given transfer function. So this is your system transfer function from which they have asked you to find out the controllable canonical form. Okay, so what is the equation with the help of which you will be able to frame the equation is given here. All right. So you need to note down what is this constant, what is this constant, what is this constant, what is this constant. Then Bn, An, B naught, all these things you have to substitute in the given formula. You will be able to get controllable canonical form. Now what are An, B naught, B1, B2, so on are nothing but, they are nothing but the coefficients of the numerator polynomial. Okay, so B naught, B1, B2, they are the coefficients of the numerator polynomial. Similarly, in the denominator polynomial, you will be having A1, A2. Alright, just to make a note of it. So, from this, tell me what is B naught, B1, B2 from this formula. This is your given system represented by the transfer function. Now, what is your B naught, what is your B1, what is your B2? Just to tell me the answer. They are nothing but coefficients of the numerator polynomial. So, what are the coefficients?
133.
Yes, 1 here, so 1. 3 here, so 3. And here 3. Similarly, this is your A1 which is equivalent to 2. This is your A2 that is equivalent to 1. Okay, just make a note of all these things. Then simple substitution you have to make in the given formula. Alright. So B, this is the N is the order. So I think it is 2. So B2 minus A2 into B naught. That will give you the first element. Similarly, this one will be B1. Like that you have to substitute. Okay. So use that in the formula. So this will be your what constant that you are substituting here? Minus An. So minus An means A2. So what is your A2 here? Here you can see n is equal to 2. So minus A1 will come here. So minus A2. So what is your A2? A2 is 1. So here you are representing this minus A2. And here comes your minus A1, that is n minus 1. So minus 2 you are substituting here. So A matrix is over. And as usual you have to write it as 0, 1. Only the last row alone has to be substituted by the coefficients. Next, as usual here also standard only 0, 1 you will be having. Now moving on to how to write C matrix, okay, from this formula, okay, all right. So B2 minus A2 into B naught. So what is your B2 here? 3 minus A2 is 1 into B naught is 1. Okay, so 3 minus 1, the answer will be 2. So 2 you are substituting here. Next thing is how to write the second one. So Bn minus 1 is B1 minus a n minus 1 is a1, and again what is the third one? b naught. B naught. So substitute what are all these values in this equation. So B1 is your 3 minus A1 is your 2 and B naught is your 1. So 3 minus 2 is 1. So that you are going to substitute as the second element. So this is what is called as what type of canonical state model? What
Controllable.
type of canonical state model is this? This is controllable canonical. Okay, controllable canonical. That's all. Next, we will learn out how to frame a observable canonical form. Directly, they have given diagonal canonical. Okay, so here they have given you one transfer function system. So they have asked you draw the or find out the state space model in diagonal canonical form. So for that the standard formula of the state model is given like this. So in this case you have to do partial fraction expansion. You need to find out the constants C1, C2, Cn minus 1, and you these are nothing but the poles that you are finding in the characteristic polynomial. All those things if you are able to find means you can easily obtain diagonal canonical. Now this is your transfer function for which you are taking partial fraction expansion. Then you are finding constants a and b, and these are nothing but p1, p2. These are c1, c2, right? Okay. So after finding this, just you are going to substitute all these things in the given formula that is found out. So here in place of C1, C2, you are to substitute A, B constants. So what are A, B constants that you are finding it out? A is minus 1 and B is equal to 3. So that you have substituted here. C1, C2, that is A, B constants. So C matrix is thus over. Then how to form B matrix? B matrix is given to be all ones here. Alright. So same way you have represented this B matrix. Now moving on to how to find the A matrix. The diagonal elements are alone formed by the roots that you find in the characteristic equation. So this is root number 1, pole number 2, up to last pole. So if you see to this equation, you find out the roots. The roots will be s plus 2 into s plus 3. So P1 will be equivalent to minus 2 and P2 will be equivalent to minus 3. So that you will be substituting is it as a diagonal element. So this sort of representation of the state space model is called as what representation? What representation?
Diagonal, ma'am.
Yes, diagonal canonical. Okay, diagonal canonical model. Okay, so for obtaining all these things, just you need to remember that basic state space model formula. Alright, and just a simple substitution will give you the answer. So there are three ways in which you can do canonical state space model. One is controllable, one is observable, and one is diagonal. Okay, so this is another problem. They have given instead of a transfer function a differential equation from which you are to substitute or find out the transfer function. So after finding out the transfer function by considering y as x1, y dot as x2, that is equivalent to x1 dot, then y double dot is equal to x1 double dot is equal to x3, that is equal to x2, like this. If you are assuming the physical variable and forming the transfer function, sorry, not that way. That will give you state space model using physical variable. Now, what you need to do here is you have to take the double time differentiation, means you have to substitute the s squared y of s. This is again a double time integration. I think this is y triple dot, mistake here. Okay, so if I am writing this equation, it will be s cube y of s plus 6 into s squared y of s plus 11 into y of s plus 6 into y of s. I think here yes, that is equivalent to 6 into u of s. Okay, now you in this side you take y of s commonly out, bring all the other terms inside the bracket, and you take the ratio y of s divided by u of s, you will be getting the transfer function. So that transfer function is 6 divided by s cube plus 6x squared plus 11s plus 6. Now they have asked you represent the system in terms of diagonal canonical form. So you need to take partial fraction expansion for this. And you need to obtain the constant C1, C2, C3. These are P1, P2, P3. Okay, find that out. All these things you have to substitute in that matrix representation that I have showed you earlier, like this. So this is your diagonal poles that you have to substitute, and as usual 1, 1, 1. And next thing C1, C2, C3 are the partial fraction expansion constants that you need to substitute. So this is another problem. All right. So this finishes off how to represent state space model in canonical form. One more topic is left out, that is pole zero cancellation in transfer function, that we'll see it now. Why people are less in number, only 30 people turned up. What is with others? Any important work they are having? Or simple bunking? Nobody is going to answer for the question. Okay, next comes here pole zero cancellation in transfer function. Again, this is your state model, that is state equation and output equation that you are having. So if you are converting that into your transfer function, the transfer function will be like this. Okay, after taking partial fraction expansion, as I have told you in diagonal canonical form, if you are taking partial fraction expansion, then it will be like this, the transfer function. Now in this equation, there are two constants, Bm and Cm. Suppose if you assume Bm takes the value of 0, then this S minus lambda I will become uncontrollable and it will become 0 and will not come in the transfer function. Suppose on the other hand, if you are considering this factor is taking 0 value, and again this factor in the denominator will become unobservable and again it will get eliminated from the transfer function finally when you are deriving it. So this is how that transfer function represents controllable and observable parts of the state variable equation they are telling you. Because just by assuming what values Bm and Cm takes, you will be able to tell whether the system is controllable or observable from the transfer function. That is what they are trying to tell by this statement. Okay. Next thing is, suppose if you are saying this is your system state space model, if I am converting that into an equivalent transfer function, then the transfer function will be looking like this. Now if I am substituting either B1 or C1 as 0, then as indicated by the previous statements, this S minus 1 factor may get cancelled. Okay. And in the same way, if you are substituting V2, C2, either one factor as 0, then this may get cancelled. It will not come at the as the final output when you are deriving the transfer function. So this is how that pole 0 is getting cancelled in the transfer function. Just by making one of the factor 0, you are cancelling out the pole. Just by making this a 0, you are cancelling out the pole. So that is what is called as pole 0 cancellation in the transfer function. Okay, and that also indicates whether the system is controllable or observable or unobservable or uncontrollable. Both are related. Now if you see to this function, this is also a state space model. Again they are converting into a transfer function. Again if you are putting in this term as 0, one of the modes may get eliminated while you are deriving the final transfer function. So this is all about pole 0 cancellation. Right, but one problem is already we have seen pole 0 cancellation in the earlier unit or this unit. So I told you first condition, if you want to cancel out one factor, if I want to cancel out this S minus 1, I have to make sure that the system is stable. And I have to make sure that I am cancelling that S minus 1 by including proper 0, correct 0. If I am including a wrong 0, then the system will become more more damaged. Okay, so that is one condition that I already told you, that is again indicated here. Suppose you are having an unstable pole, you assume, Alright. If in the denominator, if you are having s plus 1, okay, s plus 1 or s minus 1, okay, s minus 1 itself you assume. Where is this root located in the s plane, left half or right half? S is equal to 1, that is your pole, so it will be located in your right half. So if a root is located in right half, you know that the system is unstable. Alright. But if you are trying to cancel out this instability by including a pole, okay, then you have to take double care. Okay, suppose if you are choosing a wrong 0 to cancel out this s minus 1, then the system will become more double blowed up. Okay, it will become disastrous. More and more it will go to unstable. We won't know how it is becoming unstable. So that is what they are trying to tell. If you want to cancel out a pole by means of addition of a 0, then you have to take double care, especially when the system poles are unstable. Right. So this is all about pole zero cancellation. One more problem, two more problem they have given here. Yesterday I told you that this is your state space model. If you are converting that into a transfer function by using this formula that I have stated earlier, then this will be your final transfer function that you are having. But originally the system was having two modes. What are the two modes that it is having? S plus 2 and S plus 4 are the two modes. Okay. Now, but in the final transfer function derivation, what is getting cancelled here? What is getting cancelled? Okay, again I am
S
telling
plus
you,
2.
they have given one state space model, they have converted that into a transfer function by using the standard formula as I told you yesterday. The final transfer function is 1 by s plus 4. Okay, but there are two modes here as you can see. S plus 2 is one mode and S plus 4 is another mode. So if you observe the final transfer function, what mode is not present? S plus 2 is not present. So mode 2 is vanishing. Alright, that is called as what cancellation? Pole 0 cancellation in the transfer function. Okay. But while you are doing that, again I am telling you, you have to know that you are cancelling out the pole in a correct manner. If you are trying to add an inaccurate 0 and if you are trying to cancel out an unstable pole, then the effect will be more and more disastrous. Suppose if you are considering this as the state space model, again you are converting the same into a transfer function. The final thing is s plus 3. But again here you are having two modes, 1 by s plus s minus 2 or s plus 2, s plus 2, sorry, s minus 2 and s plus 3. S plus 3 and S minus 2. These are the two modes, but this is the final transfer function. So again, this is getting cancelled just in the transfer function. So this mode vanishes finally in the transfer function. Alright. So this is called as pole zero cancellation in the transfer function. Okay. That's all I think so. All the topics are covered in syllabus. Okay, with this control system syllabus is over, and I think I have forwarded three more experiments. Just you see to it. Okay, although even though it will not come for university practical, it will give you some knowledge about all those three experiments that are left out. Okay, so read through when you are free and have knowledge about it. I think I have covered up almost 98% of the syllabus. In case if I have left out any topics means they will be simple only, you can self study it. Plus the topics that I have given for assignment, that is I one standard and programming language. That programming language on seminar was conducted, that guest lecture, alright. For that purpose only they have arranged the guest lecture. Plus even if those topics are coming in test, you should be able to answer it. I am not going to teach them. It is your self-study topic, the standards and programming language. All right. I won't tell that those topics will not come. If they might come, and if they might come, based upon how you have wrote assignment, you have to give answer for it. All right. So with this control system syllabus is over. I think fourth and fifth unit are for your final exam. Okay. Again, it will be a 90-minute test only. Alright, it will not be from 9 to 10:40, it will be from 9 to 10:30 only. I don't know the question pattern. That all depends upon the course coordinator. If you miss these things in class committee, this is the thing. Syllabus for your CT3 is fourth and fifth unit. In case if you are having any doubts from your side, you can ask me. This will be your last theory class actually.